Okay, now it's working perfectly.
Brilliant.
Right.
How's Boston?
Sorry, just a second. Let me make
Sure.
sure I'm doing this. Yeah, I think Boston is fine. It's a perfectly fine place. It's currently doing that thing where it randomly decides what season it is every day.
I see.
It
Sure.
it was
Spring.
23 degrees and sunny and beautiful on Sunday, and it is currently, I believe, 10 degrees, and it was 0 degrees yesterday.
So, what kind of a US person are you? You're talking in Celsius, right?
Yes.
Oh, very
I
nice.
didn't grow
Thank
up in
you.
this country. You know this.
I know.
Celsius makes more sense. I understand. I can do Fahrenheit for our slightly more challenged American friends, but since I'm surrounded by people who speak normal degrees, I might as well actually use the standard. Okay, and we have Catherine, who is going to be our fourth co-host, so that you have sharing Patri. Hello.
Hi, Catherine.
Hello again at the right time now.
Hello.
Yes. And we'll close the whatever thing. No more waiting rooms so that people can just shuffle in as the talk begins and they can actually, and we don't have to worry about that thing interrupting our speakers. I've gotten so good at setting up the Zoom stuff. I'm so proud of myself.
So, I run a seminar and I always forget something or the other. And what I end up doing is I have these very detailed notes. Okay, now click this. Now click this. Now ask the speaker this question. And if I don't do this, then I'll definitely mess up.
I so appreciate your ability to actually remember to, like, I have a list and then I proceed to completely forget about it until the exact moment. And then I was like, where's the list? Okay, I think everything is set up. And I need this so that I can take notes. I don't know if this is only me, but every paper I've ever printed or the other thing, its back has become note paper for whatever computation or seminar I'm into. So I have all these random drafts and things with like scribbled things on the back of them currently. Uh,
Yeah.
the draft that I've been editing yesterday is now going to be the notes for you guys. Yeah.
Awkward silence before the seminar.
Always. I think we're just doing the thing where we're trying to figure out if we're like, are we doing this? Are we starting? Let's like,
Yeah, it's
I yeah, I guess we might as well start. Welcome everybody to the One Word Probability Seminar. We're very, very happy to have Nishant, Chandgotia, and Cathetine Wolfram. Nishant's going to start talk about large deviations for the 3D dimer model.
Thank you. Thank you very much, both Madam and Zoraida, for inviting me to give this talk. And it's lovely to meet friends again. I haven't traveled for a while, and it's always a pleasure to talk about this work. So this was, as already mentioned, this is all joint work with Scott Sheffield and Cathetine Wolfram. Cathetine is going to give the second talk about, if I may say, a related topic, but not quite the same. And she'll explain her model as, yeah. So it won't be a continuation of this talk, but they're definitely related in some way, which Catherine will explain. Okay, so the plan for the talk is, I'll try to explain what the dimer model is, and I'll tell you things that we know about it before our work. And then I'll show you a bunch of simulations. Then we'll start going more towards actual mathematics around this and what we found and what we did not find yet. Of course, feel free to interrupt me as I get this talk. There are 44 slides over here. I don't need to get to all of them. Okay. All right. So let's start slowly. Let's start by discussing what the dimer model is. So by the way, some quip about the pictures. If you see any pretty picture, that is probably done by Catherine or by Scott. If you see a non-pretty picture, that is probably done by me. So anyways, so what are dimers? In 2 dimensions, they are dominoes like a 1x2 block or a 2x1 block. And in 3 dimensions, they are 2x1x1 block like this. Okay, that was a very bad picture, but I hope you, okay, what happened to my, yeah. So there's your 2x1x1 block. And a tiling is a collection of these dimer tiles such that every square and cube, or every square or cube is covered exactly by one tile. Okay, so these are rectangular blocks. The vertices will land up on z square or z cube, and I want everything covered exactly once. And so the pictures look like this. If I were to zoom in, then you can see these blocks over here. And 2 dimensions, it's easier to visualize. They look like this. Okay. So that's the model. That's what a dimer is. And the question is very, very simple. What does a uniformly sampled tiling of a region look like? Okay. Before we can even make sense of this question, this is a very big question. Let's ask the following simpler question. When can a region be tiled? And the condition is given by the Hall's matching theorem. So assuming that not all of you have heard about this in the past, I'll just quickly go over it. So suppose that we are given a set R in Z3, and the question is, when can R be tiled by dimers? And the way to do this is Z3 is a bipartite graph. You divide it into 2 partite classes. And for every subset of any of the partite classes, you ask how many neighbors does it have. So for instance, if this region R is this black bounded box over here, and if I choose my set A to be these 5 dots, then you see that its neighborhood consists of 4 boxes. So neighborhood is smaller than the size of the set. And that clearly gives a necessary condition for there being a dimer tiling of this region. But it turns out that is sufficient as well, and is not terribly hard to prove. Okay, in this particular case, suppose you were trying to give a tiling. So you would put these tiles here, then you would put these tiles, and at some point you would get stuck. Now you don't have any tile that you can put over here. Anyways, so this is a very nice and simple condition, and it's true not just for Z3, it's true in fact for any bipartite graph. Great. So Hall's matching theorem is one of the very few tools that we have at our disposal for, so just give me 1 minute, trying to adjust something. Okay, I think I'm just going to make. Can everyone see the screen properly? Okay, good. So it's one of the very few tools which we have at our disposal for studying dimers in 3 dimensions. It also illustrates the importance of parity while studying this model. So now what we'll do is we'll turn this around a little bit, and we'll associate with these dimer tilings a vector field. This vector field will record the statistics of both the parity and the kind of tiles that we are using. And this is what we'll use for our LTP later. Okay, so let's go back to our picture before. So here's the Z3 lattice. Of course, I'm going to give you a 2-dimensional picture. And I'm going to label the even vertices white. So these are all labeled white. And the odd vertices are labeled black. Now, there's no tiling yet. This is just the lattice. Now I'm going to give you a unit current flowing from each white vertex to every black vertex. Okay. So every white vertex is throwing out 4 units of current. Every black vertex is taking in 4 units of current, except the ones in the boundary. Now let's put in the dimer tiling on it. So now you have these boxes, and I'm going to throw out all the the currents which don't land up on a domino. So for instance, I'm going to ignore this edge, I'm going to ignore this edge, and so on and so forth. So what this gives us is this gives us a correspondence between a dimer tiling of Z3 and a discrete vector field, where what I'm doing for each edge which is oriented from white to black, I give it current 1 if the edge belongs to the tiling and 0 otherwise. Now, okay, so this is a discrete vector field in the sense that the the field is associated with the edges of the dual lattice of Z3 in this case. But it's essentially, you can talk about it being divergence free. And it's very, there are many obvious ways in which this is essentially divergence free. One, definition of divergence free is saying that, the divergence from any particular chosen vertex is equal to 0. Now, every even vertex here, sorry, is there a question? No. Okay. So every black vertex has an incoming arrow of strength 1. Every white vertex has an outgoing arrow of strength 1. So if you deduct the right amount, if you subtract the right vector field, then you'll get something which is genuinely divergence free. And that's what you do. So by subtracting a reference flow, which is constant flow of strength 1/6 from every white to black vertex, we get a divergence free flow, where the flow out of every vertex or flow into any vertex is 0. Okay. So Now, one natural question was that when I showed you this picture of a dimer tiling, which was quite some time back, there were these various colors. What do these colors mean? These colors record the direction of the flow. So if you are looking at 3 dimensions, then you get 6 different directions. And if you're looking in 2 dimensions, then you have 4 different directions. So this is a particularly, for people who study dimers, this is a very well-known figure. It's called the Aztec diamond. And we'll come back to the Aztec diamond further along the talk. But one thing is something that you can already notice is in the Aztec diamond, if you look at this edge over here, then all the current is sort of flowing in this way. And similarly, if you look at this edge, all the current is flowing out in this way. And this is an important feature which we'll come back to. Now, this is a uniformly sampled tiling. This was simulated by Fusey on an Aztec diamond. And you can see that there are these frozen regions in the corners of the Aztec diamond. This was first proved by Jokush Propenstra in 1998. And later it was, there's a lot of work around this after their work. But particularly, I would like to point out work by Konkin and Trop, where they showed that this is a far more general phenomena. They established what is called the large deviations principle for diamond tilings in 2 dimensions. While our results draw a lot of inspiration from these results. So, I'm sweeping under the rug decades and a lot of work. I won't be able to touch upon them because the tools that they use, just to give some names, height functions, determinantal formulas, Kirschbaum theorems, local move connectors don't seem to be readily available for 3 dimensions. And so in interest of time, I will not be able to speak about them too much. But we are definitely inspired by these results. And this was a quote back from 1961, which continues to also inspire us to move forward. Okay, so now let me show you some simulations of uniformly sampled tilings of certain shapes in 3 dimensions. So this is, it's a figure, it's a 3-dimensional figure. I'll explain what it is. So at the top, you have this 2x2 box, and then you have stacks of Aztec diamonds, one below another. And you go all the way to the base of to some base, and then you go down again, down to this. And you can see some peculiarities. This is a uniformly sampled tiling. You can see that the same tile appears here. This is what is called a frozen region. And then there's this boundary between these regions, which, so it's a very curious figure. And I don't think we completely understand it. I don't think I understand it at all, where this arises from. Now, this is a similar shape where I cut that previous figure into half essentially. And now at the base of the figure, you can see that there's something very similar to what you saw in the 2-dimensional picture. Of course, there are no theorems. We don't know how to prove this. And one of the key open questions is to prove the existence of these frozen regions for uniformly sampled tilings of these particular shapes. And there are other shapes, there's which you can find in our paper. Yeah, so the simulations strongly indicate that there will be these frozen regions, but we don't know how to prove that yet. Okay, so this is sort of the introduction. Are there any questions before I start going more into the mathematics of the top?
Just a really quick technical question. What's your notion
Yes.
of duality for three-dimensional things?
So
You
I
mentioned that
was
there was a on some kind of a dual thing for three-dimensional, and there's sort of a couple of different notions you can think of there. So I wanted to...
yeah. So I'm just I did I guess if I have this as my box, I guess these are the integers, then the central vertices form another Z3 lattice.
Okay, so it's face-centered, cube-centered things that are dual. Great, thank you.
Yeah. So yeah. Okay. So let's now talk about, okay, so how do I make sense of these scaling limits? How can anyone possibly describe these limit shapes? Let's talk about these questions. So our main result is a large deviations principle of the scaling limits of diamond tilings. Let me introduce the terminology around it. So suppose R is an open set with a piecewise smooth boundary. And now you take a sequence of tileable discrete regions which converge to R in the Hausdorff topology. So you can just think you have this, I would say, these finer and finer meshes, and you're taking regions Rn which converge to R. And now recall that whenever I'm given a dimer tiling, I had this divergence-free discrete vector field associated with it. And what was this vector field capturing? It was capturing the orientation of the dimers in the tiling. So essentially, this is giving me a discrete vector field. Each tiling, uniformly sampled tiling is giving me a random divergence-free discrete vector field on the region Rn. Now, we can adapt the Wasserstein metric or the Earth-Moore metric such that the limit points of these discrete vector fields are measurable vector fields for this adapted metric. So I'll explain this a little, in more layman terms. So, okay, so there are 6 different directions associated with these dimers, right? So there's this E1 direction, minus E1 direction, E2, minus E2, and so on. And so if F1, F2, F3, so this is going to be a vector field or now on the region R. So just to be sure, this is a vector field on R, and these are on the discrete region Rn. So Fi of P, which is on the continuous region, approximates the average difference of the number of tiles in the EI direction minus the number of tiles in the minus EI direction in a neighborhood of. So, okay, this is measurable. So, this does not necessarily have a meaning, but of course you can make sense of it in the right setting. And this measurable vector field has 2 essential properties. One is that it is divergence free because it's a limit of things which are divergence free. And it is valued in this set. Why is it valued in this set? Well, it's an average of a difference of number of tiles And at a spot, you can have exactly one tile. And this is where you get this condition from. Okay. So let me repeat again. So we take these discrete, okay, so we start with tilings of finer and finer meshes, Rn. Each tiling is associated with a discrete vector field, these tiling flows. They converge to this F1, F2, F3. This is a divergence-free vector field. And Fi of P is approximately measuring the average number of tiles in the EI direction minus the number of tiles in a minus K direction. Okay, so this is quite a mouthful for if you have not seen this. So let's just look at a few very simple examples. So, okay. So here you have, half the tiles are pointing in this direction and half the tiles are pointing in this direction. So on average, you should get 0. And indeed, if you were to scale this and take the limit, you would get a 0 valued vector field. So just 1 minute. Now, in this case, you have everything pointing upwards over here and everything which is pointing downwards over here. And I might have flipped directions in my mind, but it's a flip invariant thing, so everything's fine. So the left hand will converge to 0, 1. The right hand will converge to 0, minus 1. A much more interesting example is the scaling limit of the Aztec diamond, which, in this particular case, this is precisely computed. We know precisely what the scaling limit is. And, so in these corners over here, it's, 1, 0, 0, 0, 1, and so on and so forth. So there are these constant values. Because you only see one kind of tile in this region. So we denote by AFR the set of measurable vector fields on R such that they are divergence free and they take values in the right set. Now in the metric, which I never really defined for you precisely, just because it's a little technical, but hopefully now you have some intuition for it. The space turns out to be compact under this metric. Is there a question? No. So these are called asymptotic flows. And the set O is called the set of all allowed mean currents. Okay, so this is sort of the average current in a neighborhood. That's what it's trying to capture. And so that's why it's called this set of all allowed mean currents. And this is the set of asymptotic flows. And one of our results is that all asymptotic flows are limit points of tiling flows. So you can say that, you sort of indicated that if you take these tiling flows and you take the limits, then you get asymptotic flows. But does every asymptotic flow arise as a limit of the tiling flows? And this is indeed true, and it's actually quite non-trivial to prove in our case. So these asymptotic flows are the right space to look at, to study the scaling limits of diamond tilings. Okay. So and there's also a boundary condition, which is very, very important and central in this discussion, because all these pictures of the Aztec diamond and so on, they heavily relied on what kind of a boundary I chose. So these were, to an extent, tailored. tailor-chosen is not really an English term, but they were tailor-made. Probably they were not made, they were probably discovered, whatever, tailor-realized. You know what I mean. To exhibit this kind of a behavior. So one can prove that, so boundary values are very, very important. And so one can prove that if these tiling flows converge in the Wasserstein metric to an asymptotic flow F, so this is in R, this is in R, this is on the discrete region. Now the boundary values of the tiling flows will converge to the boundary values of the asymptotic flow. And I'm again being a little vague here. What do I mean by the boundary value of a divergence-free vector field is already a question. Measurable vector field is already a question, but you know, it's a technical point. Okay, so the boundary condition B on this boundary of R measures the amount of flow going in or coming out of R. In the case F is continuous, it has the obvious interpretation, well, obvious way to calculate is just to take the inner product of F with the normal vector. We denote the space of asymptotic flows on R with the boundary condition B as AFRB. And this space also turns out to be compact. Okay, so now I've introduced two different objects. I've introduced this AFR. These were scaling limits of all tilings. And now I have this AFRB, where these are scaling limits of tilings with this particular boundary condition. So our favorite example, what is the boundary condition here? Well, you just take, in this case, it's very simple to decide, even though, yeah, so, you know, if you just take the dot product with the line over here, you get what the boundary condition is. So it's minus half here, minus half here, and half here. And so this brings us to our main result. But everything will be in this language which I introduced to you in the last few minutes. So if you have any questions, please, this is the time.
Need to ask one small question.
Please go ahead.
Thanks. Why exactly the Wasserstein metric? You show convergence in Wasserstein metric.
So why exactly the Wasserstein metric? Right. So right. So we wanted some. Okay. So first of all, large deviations is formulated in the Wasserstein metric. And you know, large deviations is very sensitive to the choice of metric that you have on the space. So that's one reason why the Wasserstein metric makes sense. We wanted a metric which would precisely capture you know, this average you know, the average flow in a neighborhood, and the Wasserstein metric was able to capture that. That's another reason. These would be the two immediate reasons that come to my head right now. Does that answer your question?
Yes.
Any other questions? Okay. So let's go ahead with our main results. So in general, the large deviations principle needs three things. One is a sequence of probability measures. That's what the large deviations principle is about. A topology or metric to say what the scaling limits are and how to compare things. And then finally a rate function, which measures, how well, these measures are close to the scaling limit that we expect it to be. And deviation from what you expect is has exponentially small probability. Okay, so now let's introduce one by one each of these objects. So we fix a open set R with a piecewise smooth boundary, and B is a nice boundary condition. Now, this is something which I really don't want to go into right now. What do I mean by a nice boundary condition? We can discuss it afterwards if you're interested. And let Rn be a sequence of regions with tileable boundary values Bn, which converges to B. So perhaps one thing I should say about nice, all the cases that you saw till now would fall under the category of nice. Okay. So Rn is a sequence of regions with, for which you get the convergence that you want. Okay, so now I can describe to you what the measures are. The sequence of probability measures that we considered are the uniform measure on all possible dimer tilings with the boundary condition Bn. Okay, so of course that's what I want to study. So this will be the measured rho n. And how do we, what's the metric or what's the topology? The metric or the topology is this Wallerstein metric, which we spoke about earlier. And then finally, the rate function. So the rate function is, okay. So this rate function, okay, this expression over here is not saying very much, except for the fact that it's a function on the set of asymptotic flows. But I'll tell you a little more about this rate function as we go along. In fact, that's more or less what I'll concentrate for, at least for the next 10 minutes. Okay, so now I have three things, where two I have described, the third one I'll describe henceforth. And this is enough to set up the large deviations principle. And so this is our main theorem. So if R is a compact region with which is the closure of a connected domain and with a piecewise smooth boundary, small b is a nice boundary condition on the region R. Now you take your discrete regions which are approximating the continuous region R, and these discrete regions, the boundary values corresponding to them converge to the boundary value on R, which is B. You take the uniform probability measure on the space of all tilings with this boundary condition, and they exhibit a large deviations principle with an n cube speed and this rate function IB, which I will tell you about very soon. And so this gives you the precise large deviation statement for dimers.
Nishant, sorry to interrupt, but
Yes.
is it clear that it's going to be, I mean, it's true, you obviously are stating it, but one as naive as me might think that the speed might be n squared because you can change a boundary and then get stuff in the volume instead. So like essentially, if you take a region of space, change things on the boundary, which one would naively think cost you n squared, the size of the boundary, and then gets by sort of changing boundary conditions, you would get something totally different in a macroscopic amount of volume. Clearly, that's not true because you prove the theorem with an n cubed there. But is there like, just given the fact that you've sort of told us that boundary conditions matter a lot here, why is it true that you can't like manufacture terrible boundary conditions and then fill in the volume from that?
You mean manufacture terrible boundary conditions which converge to B?
Something
But
different. The idea is that you
converges-
sort of you have a natural boundary conditions B, and then I take the volume, I change the thing that should cause a large deviation naively,
Uh-huh.
and then the
Hmm.
cost I should pay that should be of order n squared, not n cubed. So it seems that like this theorem tells me that seems to be impossible, at least not with the level of discernment which is continuous with respect to the Wasserstein metric.
So here's the thing. So of course you expect the number of tilings of a three-dimensional picture of a three-dimensional figure to have order n cube, exponential and n cube number of
Sure.
tilings. So that's obvious. Now, if you make any changes to the boundary, you can fall from this n cube straight down to 0. That's the nature of these dimer tilings, right? Because you can, you make this small stupid change and suddenly there's a unique tiling, maybe. And or no tiling at all.
So again,
So this large deviations is only about things converging to AFRB.
mhm.
So I'm keeping this fixed and I'm keeping this boundary condition Bn fixed. And now I'm looking at the convergence.
So but that's on my entire region, right?
That's
On all of
the
R. And then what if I have a subset of
Right.
R, something inside of it where I sort of want to induce like bad boundary conditions on that to sort of artificially freeze it, or something as the way that you're suggesting. I'm being terrible in terms of this, but it seems to be impossible, or at the very least not determinable in this topology.
Can I
Right,
can I
so-
add something? Or
Yes,
sorry,
go
if you
ahead,
still have an
Catherine.
answer. So
No, go
yeah,
ahead.
I guess somehow this is a little bit hidden in the nice condition. So even in 2 dimensions, you could try to play your same adversarial game.
Mhm.
But what happens, so basically there are boundary conditions that are sufficiently bad that they could take you from exponential growth to no tilings, right?
Right.
But morally, what's going on is that if you have any boundary condition that's not completely locked, then there's still some appreciable amount of area such that you have sort of positive entropy, such that you can, punch out, take your hole punch out a hole and retile in a fairly uniform way in that hole. And so this niceness condition, which is not actually that strong, but it's not trivial to see like what it really needs to be necessarily, is basically telling you, it is literally just saying that given my boundary conditions, given a point, if I look at a tiny neighborhood of that point, I have some entropy there. And this is satisfied by any of these sort of Aztec diamond type boundary conditions. It's sort of ruling out something very exactly what you're saying. But these conditions are also there in the large deviation principle in 2 dimensions. So it's not a consequence of the topology. It's just that, yeah, you want, as long as you have non-zero entropy at any interior point for your boundary conditions, which does not mean no frozen region there. It just means not 0 entropy, then you're good. And this is the same and not a topological thing. It's
So just to summarize what you both taught me, I'm sorry for derailing the talk, but I was very,
I'm sorry,
curious
too.
about this.
Question. This is a great question.
That when you sort of have these kind of in this world of these boundary conditions, it's not that I'm somehow these things are all close to each other and I'm losing it because of the Washington. But it's not that, just like, no, you can always take these regions. You can always have a positive, you always have an n cubed order thing. So of course your deviation is going to be n cubed because it's a sheer counting problem.
Exactly.
And I can never realize any of these terrible things in a region if I start with good boundary conditions, because that would sort of contradict that kind of.
Correct. Yeah. And
Precisely.
yeah.
Precisely.
The Wasserstein topology is hopefully not too scary. If you try to do this in 2 dimensions instead, what you could look at is, let's say you look at the gradient of the height function, and instead of looking at the soup norm, you asked, like, does the gradient of the height function converge in the weak topology?
Mhm.
This should be equivalent to the Wasserstein distance. We didn't formally check this, So I don't want to say it is, but it should be. And it is
Yeah.
equivalent to a certain kind. It is in fact equivalent to a certain kind of weak convergence for basically the average direction of a tile in a box. It is equivalent to weak convergence for that. So that's how I think about it. But it is a bit messy. Yeah. Anyway, I will stop being derailed. Thanks
Thank you
for
so
letting
much.
me comment.
Thanks a lot, Catherine. I was trying to not go too much into this nice boundary condition, but now that I have been sort of okay, so I should probably at least say what it means by nice, and this is really the key thing which makes a lot of this work. Well, okay, so right, so one thing which could be not nice. Let's start with what can be something which is not nice. Suppose we go back to this tiling region that we had before. So this was a particular choice of a tiling of a boundary condition, and this would essentially force the tiles inside. And this is something which is not nice. And nice would mean that, yeah, precisely what Catherine said, which I don't want to get into, but I think it's actually more misleading if I don't say it. So it is that if I look at any region inside, I can modify it. I can get, if there's a tiling of this region such that I can modify it and get, cubically many configurations in that region. And that's sort of the key, that's sort of the key point. And that's the reason where the niceness comes from. And that's why you get an N cube over here. Okay. So what I have not told you up until now is what this function is, the rate function is. And this rate function is closely related to an entropy function, which I will briefly describe. And this is precisely this function which captures the number of different tilings in a given region, essentially. Okay, so what's the entropy function? So again, this might be a little complicated for a person who's seeing it for the first time. It's some constant. So remember that the boundary condition is fixed. So some constant minus the integral of another entropy function. So what is this entropy function? So first, let's look at what it's taking values in. So you have a point P. This point P is in your region R. Then this is an asymptotic flow. So this is taking values in O. So these were the total mean current, the mean currents which appear in the space of dimetallics. And then we are looking at the entropy of that. This I'm integrating over the region, and that gives me the rate function. Okay. So what goes into this entropy function? It's elements of O. So, these were the values which your vector field takes. So this measured, the difference of the number of tiles going in E1 direction as in opposed to minus E1 direction and so on. And this entropy measures the exponential growth rate of the tilings of the associated flows, which converges to the constant S1, S2, S3. So now instead, this is how I envision it, that if you have this region R, and suppose you were to zoom into this region, and then you see this discrete tiling, as you zoom in, then it will essentially look like as if in that region, it has a constant flow. And this entropy function captures how many different tilings can you have of that constant flow. So what's the constant C? The constant C is the maximum of this quantity possible. Okay, so let's just quickly see some properties of this function entropy. So first of all, it's a continuous function. And it is strictly concave everywhere except the edges of this all possible values of this convex set. It equals the maximum of some specific entropy, which is also called the Kolmogorov-Sneyer entropy or Shannon entropy rate, whatever terminology you want to use, for an invariant measure on Z3 with mean current S. You apply the ergodic theorem, and you know that the average of the current exists, and you maximize on the entropy for these measures. This is achieved by an ergodic Gibbs measure. So, for instance, if you're dealing with, say, the two-dimensional Ising model, usually you have two ergodic Gibbs measures. So here you have a continuum of Gibbs measures. For each element of the octahedron, you'll have a different Gibbs measure, and possibly multiple. And so if S is an element in the interior of the octahedron, and mu is a Gibbs measure, ergodic Gibbs measure, with then ent S is equal to the entropy of this measure. And if you're on the boundary of the octahedron, then quite magically, and this was also a surprise to us, the two-dimensional lozenge tilings turn up. And this is somehow, what does the boundary of this octahedron mean? It means that you can only use three kinds of tiles, and this should remind you of lozenges if you have seen them before. And, if you look at a cube, I hope I can draw a cube properly. And if you were to look at it, say, from this direction, then you would see your lozenges turn up. Okay. This is my 10-second explanation for why lozenge tilings turn up. The truth is more complicated, but you can look at it later. Okay, so this is more or less, okay, so these are properties of the entropy function. This is how the entropy appears. And this is how we formulate our large deviation principle. So now I've sort of told you our main result. And I have 2 minutes left. Is that right, Mata?
Two to 5 minutes, depending on how flexible you want to be, something like that.
Okay. So maybe I'll give space for questions, and then I can tell you a little bit about, since there's not much time, I can tell you a little bit about how these uniform samples are created. How did we run the simulations?
Okay, I mean, first, I guess if we're pausing for questions, first of all, should we clap and applause everybody in your own space? Please thank Nishant for this wonderful talk. And if there's any more questions, we'll pause now. And if we have some more time, we'll let Nishant take an extra 5 minutes to tell us a little bit about simulations or whatever. I mean, I already bored you forever with my concerns, so I'll pass right now. And if you've got a couple of minutes, might as well take some time to tell us a little bit about sampling.
Okay. So, so one fixes a nice set Rn, and now one wants to know what a uniform tiling of Rn looks like. So the usual way of doing it, and one of the only ways I know how to do it, is to create a Markov chain whose stationary distribution is this uniform distribution. Okay, so there are other ways to do it. In fact, two-dimensional dimers are sampled in a somewhat different way. But anyways, so, and the key point here is that you want the transitions for these Markov chains to be relatively easy to generate. Two dimensions, there's this classical move called the flip move, which takes two horizontal dimers and replaces with two vertical ones, or vice versa. And it turns out, if you take any nice simply connected region, any two tilings can be connected by moves like this. Okay. In three dimensions, however, no such result is true. So this is a result by, or this is an example in this paper by Friedman, Hastings, Nayak, and Chi, which you can see that there are no two parallel dimers to flip. But of course, there are many different tilings of this 2 by 3 by, what's the other dimension? 3 parallelepiped. It's not a piped, it's a box, whatever. You could place all the dimers horizontally, vertically, for instance. So it was realized later that there's another move that one can introduce, which is called the trit. And so earlier I had two parallel dimers, which I would replace by two, parallel dimers in the other direction. But now you can think of this as a cycle of length 4, which you're moving along. And you choose this one, or you can choose this one. But now in 3 dimensions, you can have cycles of length 6. And so you have this shape. And then you can sort of cycle along that shape, and you can get two different configurations. And now if you go back to this picture, you can clearly apply this trit move over here, I believe. Okay, and you can use this to move the tiling along. And so the question which has been asked is, are tilings of boxes connected under flips and trits? For general regions, they showed that flips and trits are not enough. And by slightly modifying that example, we showed that, in fact, you can't create a set of local moves for any, for an arbitrary region. So we have examples, Rn, that if your moves only look at some radius k, then you won't be able to see all the tilings using these moves. So forget about stationarity being the uniform tilings, it's not even an irreducible Markov chain. And but for nice regions, okay, so I say nice regions here, but for nice regions like the astecahedron or this pyramidal shape, maybe the flips and trits are enough. But we don't even know this for boxes. There was some recent progress right around our paper where they showed that any tiling of a box can be modified using a flip or a trit. Now, whether it can connect you to everything, that's still unknown. Yet we can construct credible simulations, and this is an old idea, from theoretical computer science. And one would, people who are familiar with dimers would immediately see the connection. And the idea is very, very simple, that if you take two dimer tilings and you superimpose them, you have a degree 1 over here. And so when you connect them, you get degree 2. And what are degree 2 subgraphs? They are essentially cycles or double edges. That's it. But what are these cycles? The cycles are alternating from tiling 1 and tiling 2. Right? And that gives you a way of running the simulations. So how do you go about it? Suppose you were on this tiling, and now you wanted to take a step of your Markov chain. You choose a vertex on, okay, so first thing is you decide on a parity. So let's suppose we choose the parity to be this. And now I choose a vertex. I move along the dimer. Then I do a random walk. I choose randomly between the 3 available edges. And I keep on doing this walk. Wherever I hit a dimer, I move along it. And then I choose a random direction. And I keep on doing this till I hit myself back. And now I formed a cycle. And along the cycle, I alternate. And one can prove that you get the uniform distribution as the stationary distribution for this Markov chain. And this converges, but we have no idea what the rate of convergence is. So all our pictures, they're sort of, we don't know how credible they are. We think that they're very credible, but we can say provably that they're credible. The analysis is completely open, and I think this is where I would like to end again.
Thanks, Nishant. And the second clapping. Like any good math talk, there's 2 rounds of applause. We'll take a couple of minutes to pause and let Catherine set up for our second talk. I will be right back.
Oh, can people see my screen?
Yeah.
Yes.
Nice. Great. Okay, I will actually also be right back, hopefully quickly.
Do we have a speaker? Catherine, did you step out or? I think she stepped out. We'll give her a second to show up. Today I'm cheating. I get to do this from home, so I have the most comfortable possible settings. Great.
Sorry, I was.
Of course, not a problem. Are you ready?
Yeah.
Well, wonderful. We'll continue with our second talk of the day, more dimers, more fun. Catherine Wolfram from ETH Zurich is talking about the multinomial dimer model. Take it away.
All right. So yeah, thanks. I'm very happy to be able to give this talk, and especially happy to be able to give a talk right after Nishant, because couldn't be a better setting for context for this talk. So as Nishant sort of said at the beginning, what I'm talking about is not the same model, but studying this model was very much kind of inspired by stuff I did with Nishant that, I don't know, there are a lot of things that are very difficult in 3 dimensions because there are far fewer tools. And this model is sort of a variant of the dimer model where we can get back a little bit of what we lost in going from 2 to 3 dimensions for dimers, but in any dimension. So that's kind of the motivating context. So I will use the fact that I'm following Nishant's talk to say a little bit less about regular dimers. But basically, the starting point for this story is, as we saw in the last talk, if you look at uniform random dimer tilings in 2 dimensions more classically, and also in 3 dimensions, as Nishant talked about, we have this sort of incredible phenomenon that when you look at uniform random tilings, they concentrate on some particular deterministic configuration that seems to have a lot of structure. So in 2 dimensions, we can actually prove that it has a lot of structure, and there's things we actually know what this limit shape looks like, not just that it exists, that it has these frozen regions in the corners, and then is all mixed up in the middle. In 3 dimensions, what we now know is that this limit shape exists, but we can't say anything qualitative about it. So we don't currently know how to prove that it has facets, like these regions here where you see one color. We don't know how to prove that happens, even though we strongly think that it does. But there's really somehow less we can say about the limit shapes because we don't really have formulas. And so, yeah, as I kind of was paraphrasing what I wrote, what I said again, in 2 dimensions, the dimer model is solvable in the sense that you can compute stuff. So this is not a very precise term, but what I mean by it, and I'll elaborate a little bit more, is basically just that you can compute stuff explicitly. And this is just not true for the 3-dimensional dimer model, so far as we know. The methods in 2 dimensions are sort of provably broken. And so for 3-dimensional dimers, we don't have formulas like this entropy function that Nishant was describing. We don't have a formula for that, and we don't really expect there to be a nice formula. But its 2-dimensional analog actually has a nice formula. And so what I'm going to sort of talk about today is what I'm going to call a large N limit of the dimer model. So I haven't even told you what N is, so I have a lot to explain for this to make sense. But I will tell you what it is. And this large N limit of the dimer model is actually solvable in any dimension. And so that will give us access. It's a bit simplified because it's a limit, but that will give us access to be able to actually say more stuff about what the limit shapes look like, what we sort of see in any dimension. So this is my goal, is to tell you what this model is and then explain sort of an analogous theory of the fact that these limit shapes exist, which is and then tell you a little bit about what we can actually say about what they look like in this large N limit. Oh, I don't know how to use an iPad anymore. It's been too long. Okay, so first let's just start out. Let's start with the dimer model again, just as a reminder. So if you have some graph, so sometimes we draw dimers as these domino blocks when we're looking at subgraphs of ZD, but we can always take the dual picture. In that picture, we're sort of imagining each dimer is 2 cubes. So my graph is the vertices are cubes and the edges are faces. But if I want to draw this on a general graph, it's sometimes easier to just draw the dimers as edges. So dimer tiling, if I draw it like this, that is called a perfect matching instead. It's just a collection of edges such that every vertex is contained in exactly one edge of the collection. So here's this guy that Nishant showed us at the end when he was talking about this Markov chain, but it's just I'm just using it here as an example of a dimer tiling of a graph. So how do you do probability? To do probability, you have to put a measure. So in the last talk, we were always talking about uniform measure on dimer covers. And that's still going to be the sort of main setting for me, is some version of a uniform measure. But another natural thing that will be useful for me to have mentioned is what you can do is you can take on this graph, you can put an edge weight, WE, on each edge, which is just some positive number. And you can define this Boltzmann measure on dimer covers, where instead of all dimer covers being equally likely, their probability is proportional to the product of the edge weights of the edges in the tiling. So probability of a tiling is this product of edge weights divided by some normalization to make it a probability. And this normalizing constant is what we call in statistical physics a partition function. And yeah, partition functions actually contain a lot of information. So if I've made all the edge weights 1, this partition function is just the number of dimer tilings. But if the edge weights are not 1, it's some other object, but it's a perfectly natural combinatorial thing. And a natural question is, what is this number? Give me a graph, give me some edge weights, what is this number? And the somewhat amazing thing is that for planar graphs, you can compute this number. So let me explain that. So first, so Nishant told us about Hall's matching theorem, which is the true necessary and sufficient condition for checking whether a graph is tileable. And for it to be, I need my graph to be tileable for this partition function to not be 0. But an even more basic thing you can check before you check Hall's matching theorem is, okay, it's a bipartite graph, and every one of my edges contains exactly one black and one white vertex. So there have to be the same number of black and white vertices for tiling to exist. So this is not sufficient, but it is necessary that the number of black and white vertices is the same. And so what is this Castellan determinant formula? Well, the statement is that for any planar graph, you can take, so if I take a bipartite adjacency matrix, so every entry corresponds to a pair of vertices, one black and one white, and it's 0 if there's no edge there, and it's 1 if there's an edge there. You can put weights in this matrix such that taking the determinant of this matrix counts the dimer tilings. This is sort of a crazy theorem. It's actually not very hard to prove. You just have to kind of see it in the right way. If you kind of write out what is the determinant using permutations, you can convince yourself of this relatively easily. And so the main thing is somehow that when you, if you look at 2 dimer tilings, their sign when you write out the determinant as this big formula is the same. So it's a basic proof. But it's actually very powerful that we can compute this.
Why only hold
So-
for planar graph?
This is for a planar graph, yes. So I'll say something in like 2 seconds about what is the necessary condition you need for this determinant formula to work. There are versions of this, for what it's worth, for non-bipartite graphs, where you have a Pfaffian instead of a determinant. But I don't need the details of this for this talk, so I won't get into that. But the sort of slogan for like why is this cool, beyond the fact that it's just a combinatorial thing you can compute, is that surprisingly, and this will come up a bit later in the talk, you can somehow bootstrap the fact that you can just count dimer tilings to compute a bunch of other important statistical quantities about random dimer tilings. So for example, this entropy function that Nishant showed us for 3-dimensional dimers, its 2-dimensional analog can be computed using 4 determinants and taking some limit of 4 determinants of this kind. You can also compute correlation functions between different tiles. So it's kind of amazing that just by counting things, you're able to compute all these statistical things. But it's actually very powerful to be able to compute these partition functions. And yeah, so maybe to answer the question, when I said you need a planar graph, okay, so what is the real necessary and sufficient condition? This is from 1975. You can find one of these determinant formulas to count dimers if and only if your graph does not contain K33 as a minor. So this is K33. It's the bipartite complete graph. So there's 3 white vertices and 3 black vertices, and I put an edge for every pair of vertices that have opposite parity. And it's embeddable as a minor in your other graph if I can find, so I need 6 vertices. I find 6 distinct vertices, and I can embed it such that every edge of the K33 is either an edge of my graph or like a concatenation of edges of my graph. So this is not a very sophisticated picture that I made like 20 minutes before I gave a talk sometime before. And once I made it, I was never going to change it. So I think that was a while ago. But yeah, these red edges, that's just to tell you, it's not very hard to find examples that will fail. This is a very small three-dimensional graph. It's not even fully three-dimensional. It's really just like 2 layers of two-dimensional. And it's already bad because these red edges here are ones where I put it as a concatenation of edges, and the orange ones are ones where it's a single edge in the original guy. But I guess as a comment also, there's a very classic graph theory result that, K33 and K5 are the sort of obstructions to being planar. Yeah, if you're bipartite, K5 is not bipartite. So this is sort of it is very close, at least in this planar version, to being basically, the graph needs to be planar or you can't do this. Okay, so where we're going has nothing to do with determinants. So now in a moment, I'm going to tell you what this model actually is. And my slogan is that we're somehow going to get some solvability from this model, but I'm just trying to preface now that the solvability has nothing to do with determinants. It's something completely different. Also, yeah, so feel free to stop me with questions at any time, especially on Zoom. It's much easier if you just interrupt me, because otherwise I won't see that you have a question. Okay, so let me tell you what this multinomial dimer model is, so I can tell you what I mean by large M limit and all these things that I've been foreshadowing. So to define it, there's a few steps, so bear with me. So the first thing is that given a graph, I need to tell you what is the blow up of the graph. So, okay, let me make both of these. So here's the formal definition, and here's a picture where my graph is very simple, just to make the picture visible. Okay, so my graph let me explain it from the example. My graph in this example is just this line, so it's just 4 vertices and 3 edges. So obviously most of the graphs I'm thinking about are not going to be one-dimensional like this, but I need to be able to draw the picture. So what you do is you choose this bold NV, which is a vector. So it's just you choose a number, 1, 2, 3, 4, 5, some number NV for each vertex of your graph. And you blow up this vertex to NV number of vertices. So this vertex, so here my example is 3, 4, 4, 3. So this first vertex becomes 3 vertices, the next one becomes 4, 4, and 3. And then what you do is for every pair of vertices, if I take 2 guys here that were connected, I look at 2 of their lifts and I connect them. Every pair of lifts, for every vertex where, if you projected it back down, they'd be connected, they're connected upstairs. So each of these pieces here is a copy of a bipartite complete graph. So of course, as you saw on the last slide, there's going to be no determinants if I look at dimers on these crazy graphs. And yeah, so the idea is, so for what it's worth, this looks a little complicated, but for me, most of the time, NV is just going to be N. It's going to be constant. There's some previous work I'm going to cite where NV is not constant, and it can be useful to vary it, but in the theorems I'm going to state that in this talk, NV is going to be constant. So don't worry about it being so complicated. It's really just that you take each vertex, you replace it by N vertices, and you have lots of edges between them. Okay, so we're going to use this to define. Oh yeah, Nishant, go ahead.
I have a question. So is it equivalent to think of a dimer cover instead of a dimer tiling where each vertex is covered exactly n times? Is it equivalent or related?
So I will address that in a moment. So the thing is that we have to define a probability measure. So the combinatorial objects I'm going to look at in a moment are going to be equivalent to that. It's going to be cover every vertex n times. But these blow-up graphs I'm going to use to define the probability measure, because it's not going to be the uniform probability measure on these n-dimer covers. So yeah, that's a very good question. So let me tell you what the measures are. And so yeah, just as Nishant was sort of foreshadowing and asking, so what are we going to do? We take dimer covers of this crazy blow-up graph. So that means I have to take some collection of edges so that every vertex is covered exactly once. And I take this dimer cover, and if I project it back down, I get exactly what Nishant was saying, which is that because every lift has to be covered once, the number of edges hitting this vertex is exactly this NV number, this number of lifts that we specified. So if all of the NVs are if the NV is constant, then we're looking at dimer covers where every vertex is covered exactly n times. That's combinatorially the object that we're studying. But probabilistically, we want to study something slightly different. And I'll try to motivate why this is a reasonable thing to do. And I'll tell you where this is not original to the work that I'm talking about. I'll tell you about that in a moment. So this, the measures we're going to look at are, I'm going to take Boltzmann measures on these blow-up graphs. So how do I do this? This is a little bit gnarly to look at, but I put edge weights on the original graph. And for any two edges that are the lift of the same guy downstairs, okay, they get the same edge weight. Okay. And then I sample a dimer tiling here with these edge weights. And I say that the probability of that dimer tiling is proportional to the product of the edge weights. So if I have, 3 edges over this guy, then, and the weight of this edge here is WE, then I get a factor of WE cubed. This example with the single segment I've found is often confusing to people because in one dimension, you have very forced boundary conditions. Of course, there have to be 3 dimers here. But bear with me in a moment and I'll show you a different example where you don't have such a forcing. But if we project, so we have this configuration, we have a probability for each configuration. We can project them. And many configurations here will project to the same thing on the original graph. So this will give us some probability measure on the original graph on these n dimer covers, which is what we want to understand. So let me tell you what we know about it. So first, here's an example just to give you some better intuition of how this is not just uniform measure, because if this was uniform measure, this was a crazy way to introduce it. So let's just take this graph, which is the square, and I'll take all my vertex multiplicities to be 2, and all my edge weights to be 1. Okay. So if I want to take a double dimer cover of this square, there are 3 ways to do it. I can double up these 2 edges, double up these 2 edges, or put 1 edge over each one. So to figure out the probability, according to my multinomial dimer measure of each of these configurations, I have to count how many ways there are to lift this to the blow-up graph. And so we can do that. Let's do that. So if I take this one, if you look at the blow-up graph, if you choose this one or this one, what you have is that, okay, I have to pick 2 out of these edges here. So I have only 2 choices. Either they can cross or they can be parallel. And I only get that, and I get that choice twice. So I get 2 times 2, it's 4 lifts for this one, and 4 lifts for this one. But for this last one with the square, I'm picking only 1 out of these 4 edges here. So I have 4 choices. Let's say I choose this one. Actually, I have the power to draw over this drawing, so let's use that power. Let's say I choose this one. Okay, now this vertex is occupied, so it's done. We can't use this one. But this one's open, and I still have, so I've used 4 choices. I still have 2 choices. Let's say I choose this one. Okay, I'm done. But this one is open, and either endpoint is open. So again, I have 2 choices. I could choose this one. It's another 2. But then once I get to here, I don't have a choice anymore because these 2 vertices are occupied. So there's actually only 1 edge I can pick, and it has to be this one. But 16 is a lot bigger than 4. So you can already see at this very small example, even for n being very small, that these measures have this sort of preference that they want things to be sort of more evenly spread. So this is a phenomenon that we'll see. So this is my n. N is going to go to infinity. I will explain how in a moment. But we're basically going to look at n dimer covers with respect to these measures where we increase n a lot. And these measures have this kind of spreading property. Okay, so why should we look at these measures and where do they come from? So everything I'm talking about in this talk is joint work with Rick Kenyon, but a lot of the stuff that I'm talking about now is actually stuff that Rick did previously with someone else, Cosmin Pohoata. So they introduced this model. In fact, in a more general context, so it's not just dimers, but the model they introduced is actually a more general, it's any tiling model. So you don't have to take your tiles to be dimers, they can have other shapes. And you can similarly sort of do this thing where you look at tilings of this blow-up graph and project them down. And they have a whole theory of these things. And the thing they showed that makes this, one of the things that makes this interesting is that if you look at the partition functions for these things, so there's some notation here, but this is just saying, look at all the tilings of the blow-up graph, sum up all the weights. This is the same definition of the partition function that I gave you on the second slide. These things actually form a generating series in N. So again, when I write boldface N, which I can't handwrite, what I mean is a vector N, so NV, V, and V. And so when I write boldface X to the boldface N, this means like a product over V and V, XV to the NV, and N boldface N factorial is product over V, NV factorial, just to unpack this a little bit. But they form a generating series, and it's actually very clean. You just see in the end this, what we call this tiling polynomial, which is you just sum up. So the tiling polynomial is a function of X. So X is like a function on the vertices. You have an XV for each vertex, and it just spits out, you multiply the edge weight times the value of the function of the two endpoints. Okay, so this generating series, and this is not special to dimers, by the way. This works for any tiling model. And this is where we get our solvability, is from this generating series. So there are no determinants. I'll say that again, even though maybe I'm saying it too much. Instead, the place we get our solvability is we're going to look at this model as n goes to infinity. And as n goes to infinity, we can expand, we can use this generating series and asymptotic expansion to understand stuff about it. So the solvability comes from taking from this generating series and looking at an expansion. And I haven't used anything special about the graph. I haven't even used anything special about this being dimers. So this is actually very general way to sort of set up something for a large n limit. And yeah, I mean, this is a high level, just a philosophical comment. But the way I think about this is that this is sort of in analogy with these sort of large n limits in lattice gauge theory. So in lattice gauge theory, going back to like 't Hooft, maybe you want to understand, you want to do the standard model. So you want to understand like U2 and U3 and SU2 and SU3, but you can't understand these gauge groups. But it turns out you actually can understand things if you take the gauge group to be UN and you take n to infinity. And when you take n to infinity, many things about the model simplify, even in that setting, but you still see some interesting structure, and it's something where things can be understood. And there's no literal direct connection, but I think philosophically, I kind of view this as, this idea and this construction is giving you a way to take a large n limit of a tiling model, the same way that, we don't happen to have matrix groups that are indexed by a number n, so it takes more work to define such a model that depends on n. But I sort of view this as a way to add this dependence on n so that you can define limits of these models. So that's the idea. Let me tell you a little bit more, like, what does it combinatorially mean? Maybe it's a little bit confusing to think about what it means to take n to infinity in this model. So let's just take n to be constant, because that's the actual setting of my talk anyway. If you look at, I have this function m of e, which is just the multiplicity of the edge in the tiling. And this is a number between 0 and n. So if I divide it by n, it's a multiple of 1 over n, and it's between 0 and 1. So actually, for all n, this thing is a function on the edges that takes values in 0, 1. So even if I just took a subsequential limit as n goes to infinity of this thing, it's going to give me a function from the edges to 0, 1. So that's just a proof of concept. So I have a fixed finite graph. If I could take some subsequential limit of these multiplicity functions for the tiles divided by n, and this will give me some function from the edges to 0, 1. And it turns out if you look at these random ones, you can describe these random ones will concentrate around a particular function C of E. So I have to tell you something first to describe what they will be. But I'm working with a bipartite graph. So I have this bipartition to black and white vertices. And there's these special functions, which are called the critical gauge, which just solve these very simple little equations. So like, for example, So basically what you do is you just sum, I have some vertex U, which is black, and I just sum over all the white vertices V that have an edge connecting it. So let me draw a quick example. So let's say this is my U, and it has 4 edges coming out of it. Then this sum would be just over these V, V1, V2, V3, V4. And so I've got some functions f and g that are going to solve these equations. And the theorem of Rick and Cosman is that these critical gauge functions are unique up to a very simple transformation where you change, because it's a product here, like you can always slush by a constant, one of them by a constant, the other by a constant, global constant. So up to this global constant slush, these are unique. And as n goes to infinity, if I take a multinomial dimer sample with all edge weights 1, maybe I should have written that. So all the edge weights here are 1. This will converge to the critical edge weight function, which is just the product of this f and g. So if I have a fixed finite graph, then we already see some concentration as n goes to infinity on a particular sort of limiting configuration. And this limiting configuration, you can think of it as the discrete flow. It's the same kind of thing as the discrete flows that Nishant was talking about earlier. It's just that instead of taking values that are 0 or 1 on the edges, 0 or 1 discrete options, it can take any continuum value between 0 and 1 with some constraints on how they add up in vertices. There's a very analogous object to that. Okay.
Can I drop real fast?
Yeah.
Just wondering, because you said finite, and I was wondering, if I give you a nice infinite graph, can you say something similar, or is this totally hopeless?
The infinite graph is the actual result that
okay.
I worked on. Yeah, so we're getting to infinite graph very soon. Yeah, good question. For now, we're on finite graph, but we're going infinite in a couple of slides. Okay, so yeah, we have this on the fixed finite graph. Let me give you a quick example. The Aztec diamond, the same example Nishant was showing you, these critical gauge functions have kind of a miraculous formula in terms of binomial coefficients. So I just wanted to show this to you. It's kind of cool. So you can compute these critical edge weights, and they're super simple. But actually, this is one of only 2 examples that we know where these critical gauge functions have a nice formula. So it's an open question, like why are these rational numbers? And when else do you have rational numbers? When else do you have nice answers for these critical gauge? So we don't really know. So this is just a basic finite graph question, but it's already non-trivial. But I will say that even though we don't know what they are, we can't compute exact formulas in other cases. There's actually a Markov chain to compute them numerically. So I thought I would mention this, and we use this to make some pictures. But I'm not sure I will get to those pictures in this talk. But it's fairly simple. Basically, you look at this bipartite adjacency matrix for the graph. You have these equations, and you can convince yourself that basically these equations are satisfied if you can find diagonal matrices, D1 and D2, that make such that you can sort of like conjugate the adjacency matrix by D1 and D2 to make it bistochastic, which means the sums are 1 on either rows or columns. And what are the entries of the matrix? The entries of the matrix after you do this are this product, is exactly these critical weights. So you can run a Markov chain that tries to get you closer to solving these equations. And it's just a linear Markov chain. So you take A and you replace it by some D1 times A so that you get all the critical gauge equations to hold at, say, the white vertices. And then you replace that again by saying, okay, now I've done that. Now let me make it better on the black vertices and solve the critical gauge equations there, which will break them on the white vertices, but they won't be as bad as they were before the step. So somehow you can iteratively sort of try to improve on one side, on one half of the vertices, and then improve on the other half, and iterate this. And you can numerically approximate these critical gauges. So they're extremely easy to compute numerically, but they're usually not nice numbers. It's sort of a miracle that they're nice numbers for the Aztec diamond, which we don't fully understand.
So do you know cases where it's not rational?
Yeah, almost every case I can check is not rational. I know 2 cases where it's rational, but if you just choose a graph with 10 vertices and you run this, it will be clear that they're not going to be rational, or
So
it will
for
seem
example,
highly
a
unlikely.
box, for example, a box, is this already very, it's not nice?
For a box, they may all be one actually. So maybe don't do a box, but for anything interesting, it,
Mhm.
it's yeah, or a box with not with a yeah, okay. If you do free boundary conditions, sorry, if you do a torus, square torus, they're all one. If you add a boundary condition, it's not totally trivial. They may not be one because you add a 0 here, but I
Right.
don't think they're rational. Yeah.
Oh,
I'm only like 90% sure about the box because I haven't tried that example in a while. But it's either they're really boring, like they're all one, or it's slightly funny. But it's not. Yeah.
oh.
Okay. But so that's that. This ends the finite graph story. And now what we want to understand is, okay, we have this large n limit of the dimer model, which has some solvability in any dimension. Can we understand what happens in this same story where we look at these larger and larger graphs, just like Nishant was telling us about in the first talk? What do we see? Do we have this large deviation behavior where we can kind of estimate how close you are to limiting configurations? Do we have this limit shape, this unique limit shape, and so on? This is our goal. The answer will be yes, we do have a large deviation. We do have this sort of large deviation behavior. We do have a limit shape. And yeah, so this is what I need to explain to you. And then I want to tell you about what we can understand about these limit shapes, which is sort of the cool part of having more tools. So the setting of this talk will be a tiny bit more general than just ZD, but not that much. There's some balance to be had of how complicated you want to make your life with using weird lattices. But we have one nice example in a lattice that's not ZD. So you take some lattice in RD, and you can just think of ZD if you want to, but you can also think of, I take this lattice and incident to any white vertex, all the edge directions are the same. I just want something that is very, very homogeneous, just to not make things too complicated. But it could be a little more general than ZD. So we have this object called the Newton polytope, which generalizes this space of mean currents that Nishant told us about in the previous talk. So some examples, which I think I have to draw by hand because I forgot. So for Z2, oops. For Z2, this Newton polytope, if you imagine, okay, what are the edge directions? There are all these unit vectors. So the Newton polytope is this diamond. For Z3, you have 6 unit vectors. So the Newton polytope is the octahedron. So that's why it's called so this is the O of Nishant's talk. So these are just these are some basic examples of what this is. Okay. So what do we want to do? We want to play the same general. The setup for these results is really the same as in Nishant's talk. So again, we want to think of dimer covers in terms of these as basically discrete versions of vector fields. And we want to understand what their scaling limits look like when we think of them as vector fields. So, okay, I have this comment about height functions, but maybe let's not. In 2 dimensions, we also have these height functions, which we don't have in higher dimensions, but let me not dwell on that for now. As we saw in the last talk, we can instead use this correspondence with discrete flows. And this is really truly the same as it was in the previous talk. So instead of just the fact that we've added this multiplicity parameter doesn't really change anything. It's just that instead of our discrete flows on edges taking values that are only 0 or 1 with some sign, we can take values that are multiples of 1 over n, just between 0 and 1. So yeah, so I guess
just to be completely clear, you don't have a sign on this, right? It's always between 0 and 1.
Yeah, okay, so this I always so when I say the multiplicity function, I feel like it's easier to think about it if you just say it's between 0 and 1. It's a positive number, it's a multiplicity. But when you want to think about the discrete flows, we have to sort of remember the bipartition underneath and remember that all of our edges come with an orientation. If they're from white to black. And so for me, the sign is just you multiply by you change the sign as a function of the orientation of the edge. So this thing has no sign, but this thing I can define this discrete vector field from the multiplicity function by adding in the sign, basically. So if I does this make sense? Any questions by the way about this?
It makes a lot of sense.
Well, I'm not worried about Nishant. Okay. Oh, okay. Yeah, okay, so that's the end of this slide, I guess. I thought I had one more point, but I guess not. So how do I think about the scaling limits in dimension D? This is the same asymptotic flow story that Nishant told us about. So one way that I kind of like to think about this is that if you take these, if you take this guy, my discrete vector field, and I look at a vertex, and I sum, okay, I have this vertex, and I can look at all the edges incident to that vertex, which I'm writing as V plus EI. So remember that if I have a white vertex, I know all the edge directions out of it. It's some collection, E1 to ED. So if I write this V, then all the edges incident to this are V plus EI. So if I write this thing here, I'm viewing EI as a vector, then this thing is a vector. These are a bunch of numbers. These are a bunch of numbers. They're actually all positive because it's from a white vertex. These are a bunch of positive numbers between 0 and 1 being multiplied by this vector. So it's going to live in the convex hull of the vectors. Numbers actually that sum to 1, sorry. So this is some vector. And the way that I think of what we're measuring with this Wasserstein topology is that you want to look, you have this vector, and I can look at larger boxes and I can look at the average direction of this vector on large boxes. And I want this average, I want to know like in the weak topology on these vectors, whether the thing is converging. And that's basically what our Wasserstein topology is. So to give a full setup, we take these regions Rn in 1 over n times this lattice, approximating some compact region, as in Nishant's talk. So I have some blob, which is my R, and then I have some lattice region, which is my Rn. And the sort of lattice mesh scale is getting smaller and smaller. And as we take this parameter small n to infinity, the scaling limit of any of these flows is going to converge to some measurable divergence-free vector field. The same story, exactly the same story as in Nishant's talk. It's just what's changed is just like now I have a different Newton polygon because I have not specifying that the lattice is Z3. So all of this is actually completely the same as it was for the 3-dimensional dimers. There's no new complications because we've added this dependence on n. So our question, which is the same one that Nishant was talking about for the standard dimer model in 3 dimensions, is if we view it as a random divergence-free vector field, what happens when we look at this sort of iterated limit as we first take the multiplicity capital N to infinity, and then take the size of the graph small n to infinity. So we sample from these multinomial dimer measures, we take the multiplicity to infinity, so we're looking at the large n limit, and then we look at the scaling limit behavior on these infinite graphs, what happens. Okay, so let me tell you what happens. The first thing that I'm going to tell you is completely analogous to what Nishant told you, completely analogous to the Cone Canyon prop result in 2 dimensions. So we fix a region, we fix a boundary condition on its boundary. It satisfies the same niceness conditions as in Nishant's talk, which I didn't write, but I think will come up in a later slide if I get to it. We take some discrete approximation in the lattice, and we look at this multinomial dimer measure. All my edge weights are 1. I'm not dealing with edge weights. That's not the point of this talk. And I look at this iterated limit as the multiplicity, and then the size of the graph goes to infinity. And these measures will satisfy a large deviation principle where the rate function is up to a constant, this integral. And to translate from Nishant's talk, sigma is minus the entropy function. So sigma is analogous to minus this entropy function. It's not the same function because I have a slightly different problem, but it is the analogous object. And furthermore, so we have this rate function. What I'm going to tell you in like 2 slides is that we have a formula for this. In any dimension. So I'll tell you that in a moment. And what we also know is that we can also show that this thing has a unique minimizer. So we also have this limit shape phenomenon. So if you ran simulations and you looked at uniform random guys from these measures where both ends are really big, you will see something that is approximating this limit shape, just like you do for regular dimers. Okay, so let me tell you a little bit more about this rate function very briefly, and then I want to talk about limit shapes. So what's the role of this solvability? So because that was my spiel, is that we're doing this because we have a solvable model now. So the way I sort of introduced solvability earlier is that solvability was being able to compute the partition function. And the reason that that's kind of a relevant form of solvability is that what Cohn, Kenyon, and Propp showed for dimers in 2 dimensions is they showed that actually you have this surface tension sigma, their analog of that for 2-dimensional dimers. That's this thing they want to compute to be able to show a theory to show their analog of this theorem in 2 dimensions. And what they're able to show is that it is the Legendre dual of another function, which is called a free energy f. The free energy f is the partition function of dimer covers, okay, not on a planar graph, but on the torus with some periodic edge weights. And okay, the torus is not a planar graph, so you can't directly just use one Castellan determinant formula on the torus. But it turns out that you can compute the number of dimer tilings on the torus if you take 4 determinants. So my first slide, so you add up 4 determinants that basically correspond to, you imagine that you unfold your torus as a square, and the 4 determinants are keeping track of how many tiles we're crossing these identification boundaries. So you can compute this function f using 4 Castellan determinants. And then you can show by some concentration result, which is also not completely trivial. This is what Cohn, Kenyon, and Propp do, that f and sigma are Legendre duals. So they get a very explicit formula for this f from determinants, and they're able to use that to get a completely explicit formula for their analog of sigma. So this is extremely different from what we do for what Nishant talked about for 3-dimensional dimers. And the outline that Nishant talked about for 3-dimensional dimers is an equivalent approach that would work in 2 dimensions for regular dimers that doesn't involve formulas. But this approach gets you formulas. So it's a different perspective. It's interesting that they're equivalent. But what we're going to do for the multinomial dimer version is follow this same exact outline of finding this free analog of this free energy on the torus and showing that its Legendre dual is the surface tension that we care about. And because we have a way to, we sort of have the analog of the Castellan determinants in this asymptotic expansion from the generating series, that's our sort of analog. That's how it's playing the same role as the determinant formulas for our model. Okay, so what do we really show? As I said, we use this generating series for partition functions in the large N limit to compute the free energy on the torus for this multinomial dimer model. And it's a super simple function. So it's not this simple for regular dimers. It's a super simple function. It's actually analytic on all of RD. It's a log of a bunch of exponentials. Very simple. So what's the surface tension? The next thing is that we show that the surface tension is the Legendre dual of this function. And so, okay, this function is always really simple. And this function is always this Legendre dual, but that doesn't mean that this function is always really simple, actually. Of course, this is still a slightly sticky point. So in some cases, so for Z2, and for what I'll tell you in a second, there's this 3-dimensional body-centered cubic lattice. Sigma is actually really simple again. But for Z3, of course, because it is what it is. It's actually very complicated. And I actually don't know how to write it down for Z3, the sigma. This I can write down, it's super easy. This I don't know how to write down explicitly, but according to Mathematica, it seems to involve some degree of a root 8 polynomial. So we don't
It's
actually
still
have this written.
algebraic. It's still algebraic in the field generated by S and the rationals or something like that.
Yeah, I mean, yeah, it seems to, this is the worst of it. But I don't have a formula for it. Mathematica couldn't do it. By me or by Rick. So that's our current understanding is this. Okay, so let me tell you about some limit shapes and give you some examples in my last 10 to 15 minutes. So Z2, I told you the free energy is simple. This just follows from the formula I gave before. I'm writing this in slightly silly coordinates because it makes the next formula simpler, but it's a linear change of coordinates. I'm drawing my edges of Z2 on the diagonal. It's a little silly, but in these coordinates, the surface tension is super simple. It's just a sum of things that look like Shannon entropies. So in this case, it looks like a Shannon entropy. This is not in general true for this model. This is something about Z2. It's not true for Z3. So here's some graphs. So I'm comparing. So this is so let me actually click one more. So let me write some things on this slide so that you know what's what. So this is the multinomial surface tension for Z2. And this is the single dimer surface tension. So, okay, sorry, I wrote this in the wrong place. The formula below is the single dimer surface tension, but this is single dimers, the graph. So you can see it has, and this is multinomial. So the single dimer one, the multinomial dimer one is actually strictly convex everywhere on its domain. And the single dimer one has this kind of funny issue with the edges, where it becomes flat on the edges. And it has a much more, the single dimer one has a much more complicated formula involving these are called Lobachevsky functions, whereas this is a very simple formula. But it's not always this simple. We don't totally know how simple it should be in general for working lattices.
So just to be clear, in the multinomial case, the edges are still strictly convex. Because if you use two different kind of tiles, then there are just multiple ways in which you
there are many
I see.
lifts. There's basically
Many
still
lifts.
entropy to the lifting. Yeah, so even on the
Okay.
edges, you have non-zero entropy. Exactly. The vertices are the unique.
At the risk of asking a question that's going to show up in your next slide, what does this mean for limit shape?
Okay, here we go.
I'm so good.
You're so good. A fantastic prediction. Okay, so let's do the Aztec diamond, everybody's favorite example. So I mentioned there's this height function and in 2 dimensions, which we don't have in 3 dimensions, but it's useful for drawing pictures because it's a little easier to draw than a flow. So how's the height function related to the flow? It's very simple. You just rotate by, you can get the gradient of the height function by rotating the flow by 90 degrees. So what's the limit shape look like on the Aztec diamond? This turns out to be a super simple example. It turns out to be basically x squared minus y squared. This is just a change of coordinates from x squared minus y squared. So in particular, it's actually, it turns out it's actually a smooth function. And I'll say something about this later. This fact that it's a smooth function is not a coincidence. The fact that it's this simple is a coincidence. Smooth function is not a coincidence. But for example, the regular dimer limit shape is not a smooth function. The regular dimer limit shape is a smooth function in here, inside this circle. And then it has a kink, an actual singularity where it has, doesn't have a derivative, where it becomes linear on these facets. So this is a much more regularity than this. This is my first example. Let me tell you how we compute this, because there's a bunch of ways you can see how you can find this. So the first one is something that I think is actually really interesting because it's special to being this large n limit. So I mentioned earlier we have this critical gauge, which gives us these critical edge weights. And the scaling limit of the critical edge weights is also going to give us the limit shape. So if you have this formula for the critical edge weights, then you can take a scaling limit and get the limiting flow. So one way you can do it is take a scaling limit of this discrete thing. Unfortunately, we don't have closed formulas for this discrete thing for other families of graphs. We can compute it numerically, but we don't have a closed formula. So unfortunately, this is actually, this is very clean, but it's difficult to implement for other sequences of regions because we don't have a closed formula, so it's hard to take a limit. What's another way? Another classic way is actually when you have one of these variational, this large deviation principle where you have a unique minimizer for the rate function, blah, blah, blah. Another thing that is often called is it is a variational problem. So the rate function is my functional, and it has a unique critical point. And so you want to find its critical point, you just got to solve, an equation, an Euler-Lagrange equation, or a system of Euler-Lagrange equations. And for the height function, this has been studied a lot for 2D dimers. You have this, it's a gradient variational problem for the height function. And it has this very simple form. And we know what sigma is for our multinomial thing, so we can just write down the PDE. So it's like not, just to be clear, it is not the Laplace equation because of the denominators. It's not equivalent to the Laplace equation. It has these denominators, and these denominators are because the flow is forced to be valued in this Newton polygon. So like if you had the Laplace equation, you wouldn't have any restrictions on like where the thing is valued, like how big is its gradient. But our thing has a restriction on its gradient. So we're getting some kind of, but it's a pretty nice equation. I actually don't know the general theory of solutions to this equation, but it's a pretty reasonable equation. An alternate method, which I'll just mention, is that there's this tangent plane method of Rick and Istvan Prouse that lets you, for any of these gradient variational problems, find it as an envelope of kappa harmonically moving planes. So this is kappa is some function of sigma, and they have a general method for solving gradient variational problems in terms of using this kappa. So this is I think pretty cool, but also this is very two-dimensional. But we do implement this for our model. It gives us another way to compute things.
Just ask you one small question.
Of course.
Close to the end. I think that you mentioned Pfaffians, right? Instead of determinants. Where do you use them? Or could you use them here?
So for the multinomial model, they're not relevant because I'm not using any determinant formulas. But if you were working, for example, on non-planar graphs and you wanted to count dimer covers, then you would do this with a Pfaffian instead of a determinant. Dimers on non-planar graphs are still actually very poorly understood. But you do actually have this determinant formula.
Okay, thank you.
Or Pfaffian formula, my bad. Okay, so just a summary of what I've said for how we compute 2D limit shapes, so I can show you some 3D stuff and some other things. You can get an Euler-Lagrange equation, and I wrote it for the height function, but it's equivalently for the flow, but I wrote it, it's a bit of a two-dimensional equation right now. You can take the scaling limit of the critical edge weights, and this is something kind of new and exciting and cool because it's something special to our multinomial model. And you can do this tangent plane method, which gives us a general way to solve gradient variational problems. So I need to explain to you how we generalize these things to higher dimensions, just what they are in higher dimensions. So what I want to tell you is, first of all, what are the Euler-Lagrange equations? Because it's not a gradient variational problem anymore because I don't have a height function. So we have to actually work directly with the divergence-free thing, and the equation will look slightly different. And I also want to clarify what the relationship is between these critical gauge functions and the limit shape flow. So I told you can take this scaling limit of the critical edge weights and get the limit shape flow, but there's actually there's a nice way to understand this relationship, which I want to tell you. Okay, so first Euler-Lagrange equations. Our flow is divergence-free. So if you just do calculus of variations, divergence-free gives you some constraint, this divergence equation. And then for every component, every one of these, you get D choose two equations, one for each pair of distinct indices that relate basically these partial derivatives, sigma. So you have a family of equations. And when D is 2, two choose 2 is 1. And so you can get, it's actually kind of funny, you get the height function PDE, you can get the height function PDE from the second equation. Or actually, I think I want to say you can get the height function PDE comes from the divergence constraint, and this becomes the gradient constraint. It's kind of funny, they switch. but I'll say something about this again later. So to give you a quick 3D example, since I'm nearly out of time, I might move a little bit quickly. I mentioned this, we have this other 3D lattice, this body-centered cubic lattice, which you get by, you take Z3 and a dual copy of Z3. So you put a vertex in every cube, and then you just connect the original edges to the vertices to the dual vertices, and you delete all the original edges. So it's bipartite because it's pairing originals and duals. And this guy also has a very simple formula for its surface tension. So in this case, we were able to find an example like the Aztec diamond where we have this these rational critical weights. There's basically a box in this BCC lattice. Maybe I don't want to spend it's a box in this BCC lattice. It has this silly constraint just to make sure it has the same number of black and white vertices. The side lengths are like A, B, and C, but I have to take a non-square box. And for this, we have these critical gauge functions that are binomial coefficients. And so we can actually compute this scaling limit, and we get a nice, we get a divergence-free flow in limit. So this is, again, a very simple example because it's actually a little bit hard for us to come up with these examples with the critical weights. So we can't compute incredibly complicated limit shapes exactly yet at the moment, but these are some examples, even in 3D. And now with my last couple minutes, let me try to say, yeah, okay, you can check that this solves the Euler-Lagrange equations. But let me try to say a tiny bit about a step toward understanding the critical gauge. Like, what is this relationship to the limit? Because this is interesting. So there's actually a dual set of Euler-Lagrange equations. So remember, we had this Legendre duality between sigma and F. And so if we have something that solves a variational problem with sigma, then we have some dual guy related in this simple way with the gradients of these functions that solves a variational problem with F. And so when you have these, when you have this duality, you can write a, you can write a PDE for alpha instead of omega. And this is a, well, I was told, I was trying to find a reference for this, and I was told that this is a Soviet folklore theorem, and told to find some papers in Russian in some old journal, which I was not fully able to access. But it's not hard to prove it yourself. But I think this is something that's well known to a lot of people in PDEs, but was completely unknown to me completely unknown to me. But if you can turn this weird divergence-free variational problem for omega into a gradient variational problem for some other function that I call capital H. So this alpha will be the gradient of capital H, and you want to find a solution to this gradient variational problem. So this is, I call this the gauge Euler-Lagrange equation. And to be clear, even in 2 dimensions, this capital H is not the height function. It is a completely different object. This function exists, for example, for regular 2-dimensional dimers, but it is a totally different function. And it turns out that this function is the scaling limit of our critical gauge functions. So what you can check, and this is sort of by some kind of maximum principle argument, that if you take either one of these two critical gauge functions, and you look at the 1/n log of limit, it will converge to the solution to this other PDE. This maybe explains a little bit what the critical gauge functions are and why they are related. And you can also compute in examples what this function is. So for example, for the Aztec diamond, here it is. You can check because we explicitly know F, and then here's H. What is a gradient F of gradient of H? And you can recover the divergence-free flow we saw earlier. So this is something I think, this is something I think is interesting even in the standard dimer case. We don't actually understand we don't have a discrete version of it, right? Here we have this discrete version because we're looking at the large n limit, but this H actually still makes sense even for regular dimers. All right, the last thing I'll say, which I'm going to try to say in like 1 minute, Nishant showed us that we have, or we at least expect to have these facets in regular dimers. And the last result I want to show you is, okay, we saw that these large n limit dimer limit shapes look kind of smoother. They don't really look like they have these. And it's actually a theorem that they don't have them. So add in this, you have to add in this condition, which is actually the same as the condition of our large deviation principle, that we don't want stuff where all the tiling itself is completely fixed. So like, let's say here, all these tiles that I colored are determined in this sort of order that I colored them. So if you have something like that, you just have to throw it away because that's no good. That will be frozen, but throw that away. If you throw that away, then the multinomial dimer limit shapes in this large N limit do not have facets. This is a theorem. And conjecture, which is a slightly bold conjecture, but that I actually do think is true, is that for any finite n, these multinomial limit shapes do have facets, but they're like shrinking in size as you take n to infinity. So if I were to draw like the Aztec diamond, you know, for n equals 1, you see this and you see these 4 frozen regions. As you increase n, I sort of imagine that this middle circular section becomes less, sort of grows outward. And when you take n to infinity, it fills the whole thing. And yeah, there's a sort of, it's not actually complicated to show this result, but maybe I will skip that and just say thank you for listening. Sorry for being actually a whole hour.
The whole hour. Thank you very much. Applause at home. Everybody do your thing and thing. If there are any quick questions, unfortunately, I have to run in a couple of minutes to teach, so I'm going to have to keep it short. But if there's any questions.
Or additionally ask, hopefully any other as well, that on still, how to study this in dimensions higher than 3 for both.
Our results hold in any dimension D.
Any dimension. All of the analysis. Or
yes.
All.
Yeah. So
the whole thing.
Yeah, go ahead, Cassie.
Well, in the multinomial setting, it's actually written completely for arbitrary dimension D. In the 3-dimensional dimer setting, I think we hope that things can be modified to work in dimension D, but it is written for dimension 3. But in this case, it is completely written in arbitrary dimension.
Yeah, we expect that all the complications which are to arise, they already arise in dimension 3, but we haven't explicitly done any calculation in any other dimension, I guess.
Yeah, there would be some non-trivial technical work in the standard dimer case to, for example, prove it in 4 dimensions. We expect that the outline to be identical, but the proofs are not. The details are real. Whereas in this case, it's all the same. It doesn't depend.
With that comical understatement of technical difficulties, I think we'll end it for this week, and hopefully we'll see you guys in 2 weeks for the final one probability seminar of the semester. Thank you. Thanks to the speakers, and thanks to everyone who came.
Yeah, thank you. Good
Thank
to
you
see
guys so much.
Thank you.
I obviously had a great time, but I think it was a great talk. I'll hope